Okay, hello everyone, and welcome to today's lecture. So, this lecture is our last lecture before the midterm exam. So, whatever we cover and up till today, including today, that will be covered in your midterm exam. And if not today, by tomorrow, I will release the practice midterm exam. So, you guys can start solving it on your own. And then on the Thursday class, I will walk you through the solution of that practice exam. Okay. So having said that, let's start our today's set of slide. Today we are starting a new topic which is about threads and concurrency. Last time we finished our discussion about processes and we said that we're assuming a process, a single-threaded process. So now let's talk about what it means when we say a thread or what it means to have multi-threaded processes. So in today's lecture, we will introduce ourselves to the notion of a thread, which is a fundamental unit of CPU utilization, and it forms the basis of multi-threaded computer systems. So we will identify challenges of multi-threaded programming. So in the outline, we will first go through the motivation for thread abstraction. Then we will discuss challenges of multi-threaded programming and Amdahl's law. And then at the end, we will talk about how threading support is implemented, right? What are the options available for implementing threading support? So today's slide, it will cover the course learning objective 5. Okay, there is a mistake, which let me correct it right now. Okay, so, and the objective 5, which is basically building the ability of analyzing, evaluating, and implementing threads. Okay, so why we need threads? Let's try to understand through a motivating example. Assume that, let's say, you have an word processing application, and this application need to do multiple tasks simultaneously. So, for example, the first task is to monitor the keystrokes, which basically are the characters which are entered by a user. Task 2 is responsible for updating the display, like after the data is read. So display should also be updated. And the third task is to do spell and grammar check. But we want all these three tasks to be performed simultaneously, right? So at a conceptual level, it looks like this. So if we try to write our write program of our application using the knowledge which we have gathered until this point in this course, then this is how our code will look like at a pseudocode level. So you have a main function, and then what you can do is like you can call three functions, each one to responsible for performing the given task, like task 1, task 2, and task 3, right? But this is not what we want to do, because if we invoke three functions in sequence, they will be executed one after the other. But we don't want these tasks to be performed in a sequential fashion. We want them to be performed simultaneously at the same time, right? So then, how can we have these multiple tasks performed? How we can perform them simultaneously? So one option is that we can launch three separate processes, because until this point we have knowledge only about processes, right? We have no knowledge about threads. So what we can do is that we can launch three separate processes, and then we can assign each task to a process separately. Uh, but if we do that, it will look like in memory, the layout of these three processes, let's say P1, P2, and P3, it will look like this. Each process will have its own address space where every one of them have their own text, data, heap, and stack segments, right? But it results in more memory consumption. So three processes meaning three different address spaces, which means occupying more memory space. And also we need to maintain more metadata. For example, process control blocks or PCBs. So it will look like for example, in context of Linux, it will look like you have a linked list of the process control blocks where you have one process control block for each process separately. So uh, give me some 1 minute. I will be back. Sorry guys for the disturbance. So if we say that okay, we can allocate one task to each process, then it means that we are occupying more memory and we are also need to maintain more metadata, right? So, but if we look at the address space of these processes, so we can make the following observations. First, that uh, remember, if I let me go back to the take you back to this slide. So here we are saying that task one, task two, and task three, these are functions, and which mean these are the function in the same address space. They belong to the same process, right? This is one process and it is executing the function task one, task two, and task three. But then we are suggesting, okay, we can replace task one by a new process uh, like and so it's mean that this new process will share the address space with the parent process. Why? Because we want this new process only to perform the task one, right? And the second child, we want it will also share the address. It will not share the address space, but it will have the duplicate address space as the parent. And then from that address space, it will execute only task two. And the third child, it will also have a copy of the same address space as the parent. And from that duplicate, it will execute only the function task three, right? Is everyone with me? Everyone agrees with what I'm stating, or if you have a different opinion? If you have different opinion, or if you have a question or confusion, let me know. Okay, so that's why we said that when we will create these processes P1, P2, and P3, they will have the same duplicate of the address space of the parent. Parent address space is not shown in the figure, right? Uh, but then they are occupying each one of them having their own address space, mean we are consuming more memory. But the observations we can make is the following, that all three processes, they operate on the same global and dynamically allocated data. Why? Uh, because we are assuming that they are performing different operations but on the same task. For example, the one which is displaying task 2, which is displaying the data, and the task 3, which is doing the spelling and grammar check, they are actually operating on the same data. The same data is displayed by task 2 on the screen, and task 3 is performing spelling and grammar on the same data, right? Grammar check on the same data. So it's mean that they are using the same global and dynamically allocated data. And the code segment is also the text segment is also same. The only difference is that process P1 will execute task 1, function task 1. I'm writing only T1 for that. Task 1 from the text segment. P2 will execute the function T2 from the text segment, and the process P3 will execute task T3 from the text segment, right? So what we and they also since they are a process P1 is executing a different task, P2 is executing different task, and P3 is executing different task, T3, it's mean that and when we say task, basically they are functions. So since they are calling different functions, they will be maintaining their own local variables, right? So remember that any variables within the body of a function, they are considered as the local variables of that functions. So it means that the address space of these three processes, it will have exact same copy of heap and data, but the only difference will be in like stack and the code segment, which is like code segment only in the sense that they will be executing different sections of the code segment, like T1, T2, and T3, right? So So what we see here that basically we are maintaining the separate copies of the same text, data, or heap segment in memory, and by that we are wasting the memory. So for example, this heap segment, it is duplicated 3 times here, right? And the content of this heap segment is same across all three processes. Content of data segment is same across all three processes. Content of text segment is also same across all three processes, right? So we are like by like creating three duplicate copies, we are wasting the memory. However, the stack is not same. Why? Because we want these processes to execute three different functions: task 1, task 2, and task 3. Different functions mean different variables. So as a result, the content of the stack segment will be different. So stack will not be same across three address spaces. So with that, we can make an argument that instead of maintaining separate copies of heap data and text for all three processes, we can share heap data and text among all three processes, and then they can have only their how to say unique versions of stacks, right? So that is, we can have text, data, and heap and files. Anything which is shared, we can have single copy of that. And as a result, we can reduce the overall memory footprint print of the application, and we can also reduce the size of the metadata to be maintained. Okay. However, the issue is that one process cannot access heap data text files of another process as they maintain different address spaces. Uh, are you guys with me on this or not? What I'm trying to say is, like, even if I say, okay, let me go back to the OneNote. Okay. So here we said that we can, so let's say you have this main process. And then we said that instead of calling three functions, task 1, task 2, task 3, it can create three processes. And then those three processes can execute the function task 1, task 2, and task 3. So let's say we create three processes. And if we create three processes, each one of them will have their own uh, address space, like process A, process B, and process C. So remember, when we create a new process, at least in Linux, then initially it has the same exact address space as the parent. So since process A, B, and C are children of parent, so same address space, I'm naming it as process main. So exact same address space will be copied over, right? So I don't want to draw the internal segment like text, data, stack, and heap, okay, because it will take time, right? So uh, or let's say let's say text, data, heap, and stack. Now, as so initially everything is same, right? And but then we say process A executes uh, T1 from the text segment. This executes T2. This executes T3, right? It's mean that if process A executes T1, the stack content will be different. will become different as compared to all other processes, right? But data heap, they are same, and even text segment is same. So T1 is just a function within the text segment, right? Now we can, since they are common, these are common, these three sections are common, what we are suggesting is that we can have one parent process PM, and these A, B, and C, when we create them, instead of like having their own text and that text data and heap section, they can have only one section, which is stack, right? Or maybe if you want just to like to be visually correct, we can say that it can have only stack, process A, only stack, because stacks are different. Process B, it has only its own stack, and process C, it has its own stack, right? And for heap data and text, they can access the same heap data and text segment of the parent process, which is process main. However, this is not possible. Why it is not possible? Because one process can never access the address layout or the memory of another process. So process A, B, and C, they cannot access these heap data and text segments of the parent, right? So then what is the way, around? What is the solution where we also want to have low memory utilization, a low memory footprint, but also want these processes A, B, and C to share heap data and text, right? So, one process cannot access heap data, right? So what we can do is that we can actually create threads, and threads make this possible, that they can share the heap data and text segment, but each thread then have its own stack and own local variables. Okay. So threads which belong to the same process, they share code, data, and files. So this is what we wanted to do. Sharing of code and data and the heap segment even, which actually is like files can be mapped into the heap if we use memory mapping. But anyway, and then we also wanted to have thread specific program counter, registers, and stack, right? So what we wanted to achieve, that becomes possible through the abstraction or through the concept of threads. So this is shown here. On the left side, you have three processes, P1, P2, and P3. Each one of them have their own address space. But on the right, you have a single process, and then a single process has three threads. And then all these three threads, they share code, data, and files, but all of them have their own registers, stack, and PC. Stack section, register, and program counter. Okay. Any questions until this point?
So in short, each process is its own thread built off of the code, data, and files that they all share.
Say it again, please.
So each process is its own thread and it's built off of the code, data, and files that they all share, kind of,
Yeah.
more or less.
Yeah, each process can have at least one thread. Actually, it must have at least one thread. And
Right, to keep them
then,
separated.
yeah, but then it can have even more than one if it is a multi-threaded process. But in that case, if it is a multi-threaded process, then those threads, they will share code, data, and files, but they will not share register, stack, and PC. Each one of them have
Right.
register
Those are
stack.
the its own section that makes up its thread.
Yeah. Uh, and someone, okay. Okay. Any other comments, question? No? So thread is a basic unit of CPU utilization. So what does we mean by this? So it means that cores, they are given, or they are allocated to threads, not to processes. So uh, from the perspective of the operating system, uh, threads are like considered, even like if you have, let's say, three threads in a process, so each thread will be considered as a standalone process. And as a result of having threads, we achieve responsiveness. Because, for example, if we can again go back to our example, word processing processing application. So let's say the way we had two threads or three threads, one is responsible for displaying, other responsible for reading the keystrokes, and the third responsible for performing grammar check. So let's say if reading keystroke is not slowed, so it's slowed down. So here what happens, like let's say if the thread which is responsible for performing the spelling check, if it is slow, but then it will not affect the execution of the thread which is responsible for handling the keystrokes. So as a result, our application will still become responsive, will appear responsive to the user. Now compare it with the case where you had only a single thread, which is responsible for performing the spelling check, for handling the keystrokes, for displaying the data. Now, if performing the spelling check is taking long time, then it's mean that keys which are entered by the user, they will not be read, or the speed at which they are read will be slowed down. And as a result, the user will experience that his program is becoming less responsive. Okay. So that is an advantage of having multi-threaded applications, that it increases the responsiveness of the applications. Also, it makes easier to share the resources. For example, remember in last lecture uh, we talked about communication between processes, and we mentioned two different ways, like memory sharing and also message passing. Now, in case of memory sharing, for example, if you want to want to achieve communication between two processes through memory sharing, you need to first you first need to create a shared memory and then attach it in the address space of the processes, right? So, which means you need to do extra work for communication, or for resource sharing or memory sharing. But if it comes to the threads of the same process, you don't need to do anything. Why? Because already your data segment is already shared, your files are already shared. So when data segment is shared, it's mean that all the threads can access the data segment, and which mean basically that memory sharing is allowed. Similarly, files are shared, so all threads of the same process can access the same files. So let's say if thread 1 opens the file 1, thread 2 will be also able to read or write to the file 1. Uh, it As a result of multi-threaded application, we have lower memory space as compared to the case where we replace each thread with a separate process, just like I explained in the previous slides. And therefore, we have lower memory consumption, or smaller memory footprint. And also, it is much faster to do context switching between threads as compared to the context switching between processes. Uh, can anybody give me a answer why it is faster to do the context switching between threads as compared to the processes? We haven't discussed it, but what is your educated guess? Why we are claiming here that context switching between threads is much faster as compared to context switching between two processes? Okay, is it because they share code data and files? Uh, y- True to some sense, because remember that when for each process we maintain one process control block, right? And what we have in that process control block, all the information related to the process which is needed to, for example, restore that process in future once it is suspended or put in the waiting state, right? Similarly, for each thread, we also maintain the thread control block. right? And it also contains all the information which is needed to resume that thread in future. But since each thread has lesser amount of metadata as compared to a process, because it is sharing some of the information or some of the components with all other threads, that's why the size of the thread control block is smaller than the process control block. So it takes much less time to save the thread control block in memory and then restore it from the memory when we need to resume the thread. That's why the context switching is faster. Keep in mind that figure which we discussed last time about context switching. Whenever context switch happen between two processes, you need to store the process control block of one process and then restore the information from the process control block of the other process, which takes time. Also, multi-threaded applications, they are more scalable as compared to the case where you want to do the same thing want to achieve the same functionality using multiple processes. And the reason for that is because multiple threads, they share code, data, and files. So, for example, if we have three processes instead of three threads, then each one of them will also have their individual code, data, files, stack, and heap segment, right? Uh, which actually increases the memory requirement. So as you increase, as you keep creating more and more processes, you are consuming more and more memory. So it's mean that your memory consumption becomes higher. But when you compare it with the number of threads, your memory consumption is lower. That's why we say that they are more scalable. So single thread application can run on one core while multi-threaded applications run on multiple cores. Uh, as long as the number of threads are less than or equal to number of cores. Uh, this is like another angle to look at the situation. So for example, if you have a single application, uh, then remember, if you have an application which is like single threaded, then it means that it can run only on a single core. However, if you divide it into three threads, then you can run each thread on a single core, on a different core. So if you run on three different cores, these threads on three different cores, it's mean you are able to speed up the execution of your process. So it like completes its job in you complete the functionality in lesser amount of time. Okay, now if we go back over to our motivating examples, so now we can say that uh, if we want to do the three tasks simultaneously, then instead of calling three functions, we need to create three methods, to create three threads, and then ask those three threads to perform those three tasks separately, but in a simultaneous way, right? Any questions at this point? Okay, let's now try to understand the relationship between threads and cores. Before I go through the slide, let me state this, that a thread is a software concept, right? But uh, you need a hardware core to let a thread execute. And from the OS perspective, each thread is handled as a process. So like if you have, let's say in one case you have an application which is single threaded, then it will be handled as a single process by the OS. Now let's say in another situation you have a process with four threads, but so it is like four threaded application. So to operating system, it will appear like there are four processes running, and then each process can run on a separate core. So actually OS will schedule each process on a separate core, assuming we have at least four cores available. Okay, so let's say we have a single core CPU, and then I ask you this question, can we achieve concurrency What does it mean? Let me first explain what is concurrency. Can we achieve concurrency and can we achieve parallelism? So what is concurrency? Concurrency means that we allow multiple tasks to execute over time. So now, if you know what now after you know what concurrency is, which basically mean interleaving the tasks, right? So now if we have a single core, can we achieve, can we perform multiple tasks in a concurrent way or not? Anyone who want to answer?
I
Let me
assume
repeat.
not, because each thread requires a core, no? To run a separate core.
Uh, yeah, let me again state what concurrency is. So here it says concurrency means allowing multiple tasks to execute over time, or in other words, to interleave tasks for execution on the same core. So with that, okay, what will be your answer? Do you still think we cannot achieve concurrency, or do you think we can achieve concurrency?
Over time, yeah, but I
Yeah,
guess at the same time, possibly
okay.
not.
Yeah, Asim, you wanted to say something?
Yeah, I think we can concurrently run multiple processes. You can like keep multiple processes in the memory and like switch between them. And once you like switch from one process to the other, you save the context of that process.
Yeah,
In that way, with a single core, like you can run multiple processes
yeah,
without like wasting CPU cycles, I guess. It's not true, like you're not running them at the same time. You're just switching so fast that it seems you're
yeah.
running multiple stuff at the same
Yeah.
time.
Yeah, that's true. So if you have a single core and you need to perform multiple tasks, so you can run them in a concurrent fashion or in a concurrent way, because what you are doing is that simply you are doing the time interleaving. So for example, first you allow T1 to run for some time, and then you allow T2 and T3 and T4, and then go back T1, T2, T3. Like this is just one option, like how to schedule them like in round robin fashion, T1, T2, T3, 4. But the thing is like we are interleaving them, but at any given time, only one task is running, right? So yes, by letting scheduler to interleave the task, we can achieve the concurrency. Now compare it with the parallelism. So what the parallelism is? Parallelism is letting multiple tasks to execute simultaneously. Now, if we have a single core, can we achieve the parallelism?
I think that requires multiple cores.
Yeah, so it will not be possible because our requirement is that they are run at the same, that they are executed at the same time. So like for example, if we have core 1 and core 2, if we have two cores in our system and we want to run four tasks, then what we can do is that we can run T1 and T2 at the same time but on different cores, and then in next time slot we can run T3 and T4 on two different cores, right? So we are doing in time interleaving on core 1, or we are doing the we are achieving concurrency, but we are also achieving parallelism across two cores. So this is the difference between concurrency and parallelism. So this is also an example of the case when software abstraction needs hardware support. What does it mean? It means like if you have, let's say if you have four threads, but your hardware supports only a single core, you cannot achieve performance improvement because you can run only one thread at a time on a core, right? So if you, so you have the software abstraction of a software idea of how to say thread, but your hardware doesn't support the execution of more than one thread at a given time, so it is of no use. So in order to like benefit from it, you should have also more than one core. So then you can allow, for example, two threads to execute at any given time. Okay, so now we said that okay, we can achieve performance improvement. We can make our performance scalable by creating more and more threads, right? But it is not always the case that we can create threads. We can convert our application into multi-threaded program or into multi-threaded application. Why? Because for that we need to first uh, uh, identify the tasks which can be performed simultaneously, right? So, and this is like, so basically you want to convert your application into multi-threaded. So which means you need to now convert your application or write your application by using the ideas of a paradigm of the parallel programming. So for that, first you need to do is to identify the task which can be performed simultaneously. For example, let's say you have an application which finds sum of all elements in an array, right? Like let's say 1 to 12. So you can easily divide it into multiple tasks. Let's say you can divide into 4 tasks, and the first job of the first task is to sum only first 3 numbers, task to sum the next 3 numbers, and so on. And then at the end you find the sum of you sum together all the partial sums coming from 4 different tasks and then get the overall result, right? But it may not be possible to identify the parallelizable task all the time. So for example, let's say you consider you have another application which updates all elements in a sequence such that new value of an element is equal to its old value plus 2 left elements. So for example, if we have this array 1 2 3 4 5 up to 12, so the new value of 2 next element 2 is its old value plus 2 elements on the left side, so which is basically 2 plus 1 3, and for 3 it will be 3 plus 2 elements on the left side, these left side, because these are the new values of the array. So 3 plus 4 is 7, 3 plus 3 plus 1 is 7, right? And for 4 it will be like 4 plus 7 plus 3, which is 14, right? So now the thing here I want to highlight is that you cannot find or calculate the value of the next element without calculating the values of the or independent of the previous values of the values of previous element, right? So which means you must perform the computation in a sequence, like from left to right, one by one. So you cannot parallelize this, at least to me it looks like you cannot parallelize this task. Maybe there is some clever way to do that, but it is not trivial, at least, right? So if that is the case, then you cannot if you cannot break it into, like, let's say 2 or 4 tasks, and then you cannot parallelize it. And if you cannot parallelize it, then you cannot convert your application into multi-threaded form. The other thing is that only identifying parallel task is not enough for achieving the good performance. What you need to do is that you also need to do the task balancing. So let me try to explain again using the same application. So one option is like you want to find the sum of all elements. So in the first case, we are like converting into 4 tasks, and each task is operating on the same data set, like data set of the same size, like 3 elements, right? Now let's say I have another case where I identify 2 tasks. The first task operates on the 3 elements, and the remaining task operates on 9 elements, right? 4 to 12. But this is not task balancing. uh, why? Because we are allocating more computation to task 2 as compared to task 1, and this is bad. Why is why it is bad, or why task balancing is important? Because if we are not balancing the task in terms of the computation they perform, then we will end up with underutilization, of course, because the task which is, let's say this is task 2 is run by thread 2, and task 1 is run by thread 1. Now the thread 1, which is running, let's say, on core 1, will complete earlier, but the thread 2 which is running on, let's say, core 2, will complete later, right? So while core thread 2 is running, core 1 will be wasted, right? But if we compare it with the case where we equally divide, for example, here, if we equally divide, then both of them will complete their execution almost in the same amount of time, right? And as a result of this underutilization of core, our overall result will become available with more delay. Any questions here? Okay. Uh, other than task balancing, so task balancing basically focuses on the on equally distributing the computation to threads, right? But data splitting, it talks about splitting the data and then assigning it to the task in such a way that it helps in quicker execution of those tasks. What does I mean? What do I mean by that? So for example, again, we have the same application. We want to find sum of all elements. So how can I separate the data? One possible option is that I ask task one, which is performed by thread one, let's say, to operate on data one, two, and three. So which is located in memory in sequence, right? And then I ask task thread 2, which is performing task 2 to operate on data 4, 5, and 6. Now compare it with the situation where thread 1 operates on the data 7, 1, 4, thread 2 operates on the data 8 to 5, thread 3 operates data 9, 11, 3, 10 2, and thread 4 operates on 10, 2, and 6, right? Now, if you compare these two different approaches of splitting the data among the threads on which those threads perform their tasks, what is your what is your comment or what is your understanding in terms of like which data allocation or data splitting is better as compared to the other in terms of achieving in high performance or completing the task in lower amount of time? Anyone who want to answer? So let me rephrase the question to make it simpler. Do you think, so suppose that this array is located in memory, right? And then definitely there is memory at the end here because caches, they read the data from memory, and here also at the bottom there is memory, right? So which scheme will complete the task earlier? First scheme or the second one? First is on the top, second is in the bottom. So first, where the data allocation is in sequence 1, 2, 3 for thread 1, 2, 4, 5, 6 in thread 2, 7, 8, 9 for thread 3, and 10, 11, 12 for thread actually it should be 4. Yeah, right. Will this result in faster completion of all the tasks, or will this result in the faster completion? Anyone want to answer now?
I don't think there'd be a difference, right? Because they're doing the same thing. It's just the order of the numbers would be different, right?
Mhm. Okay, so someone else has also responded. Let me take that answer and then I will comment back. I think approach 2 would be better as it randomly picks the numbers first approach sorts them, which will be time consuming. Rupak, you are saying that first approach sorts the elements. No, to start with, elements are already in sorted form in the memory, so tasks don't need to sort them. Okay, and let me give you a hint that it has to do something with data locality. Okay, then let me explain it to you. So since we are saying that data is located in memory, like here in sequence 1, 2, 3 up to 12, right? So if I say that, okay, thread 1 running on core 1 will operate on 1, 2, and 3, so it's mean that it first need to read the data element 1. But remember that when it reads 1, it will, as a result of data locality, the next element will be brought in. Maybe not only next one element, but maybe next two elements will be brought in, or next four. It depends upon prefetching schemes in the hardware, right? So if it prefetches 1, 2, and 3, so when it reads 1, 2, and 3 also read on, so it's mean that when it processes 2 and 3, it will take less time because they are already in the cache, right? Same is the case for thread 2. It reads 4, And when it reads 4 from the memory, the also element 5 and 6, they are brought in to L1 cache from the memory. So when actually the thread wants to access 5 and 6, they are already in the cache and they are not read from the memory. And same goes for thread 3 and thread 4, right? Now compare it with the second case. So core 1, it accesses 7. So if it accesses 7, so and if the array is in sequence in memory, it's mean that here it will bring it 8 and 9, right? But after reading 7, it need to access 1, but then it sees it is not in L1 cache. So it will go down to the memory and read one from element 1 from the memory, which will take more time. So when it will read 1, uh, it will also fetch in 2 and 3. But next time it wants 4 and 4 is not there. So it go down to memory again, right? So it will take more time. So basically what I'm saying is that the way you separate the data among the tasks, it also affects the time or how long it takes for the task to complete. So for example, here, if you can benefit from the data locality, you will be able to complete the task faster. But if the data allocated to each task is like not in sequence but in random locations, then it will not be able to benefit from the data locality. Okay. Any questions?
Sorry, could you please elaborate on the prefetching thing? So, when you're getting data from the memory, is the data like fetched in batches or is it fetched like individually? Say, is it fetched as a block of 1, 2, 3, or is it just 1 and then 2 and then 3? Like, I don't
Okay.
understand what the
Okay.
mechanism.
Okay, let me explain. So let's use the same example, right? Uh, so let's use the same example. Let's say we have this an array of data and right. I don't know. Let's say each element is, I'm just naming A, B to Z or whatever. And this data is located, sorry. And this data is located in memory, right? Now, let's say you are running a program and it says for I is equal to 0 up till, I don't know, up to like starting, I'm just starting pseudocode from I is less than equal to Z and I plus plus, right? Uh, and I'm naming this as array. So simply set array I equal to array I plus. So simply increment it, right? Increment and put it back. Okay. So here what you are doing. So what you are doing is like you are saying, okay, just read every element of the array and then increment its value and put it back, right? So now consider the hardware you have here. This is memory which contains the array. This is L1, this is L2, and this is your core, which is running your code, right? So when you say, okay, the one thing is like okay, so when you want to increment A, so first you read A to from memory to L2, then from L2 to L1, and then from L1 it goes to the registers in the core, and then you increment it and then you write it back, right? So let's say it becomes A plus plus, I don't know. Okay. Now, next time when you need to process the next element, you go down to the memory again, you read B, you put then B in L1 and then to the registers and then increment and put back in L1. And then you read C from memory and put in L2, L1, bring it to the registers and increment and put back in L1. So this basically we are saying that every time we are reading one element from the memory, bringing it up to L1 and then processing it, right? Now compare it with the situation where we say that, okay, we are using a prefetcher. So prefetcher is a hardware component in our processor. So what does it do is that when you say, okay, read A from the memory, so then it reads not only A, it also read the consecutive next memory bytes. So it reads, let's say, now how many consecutive next memory bytes? Uh, it can vary. It depends upon like how far you want to prefetch, or what is your what type of prefetcher you are using. Let's say we are assuming that we read the next only next byte, right? So we are reading when we need to access A, so it prefetches also B. And so here you have A and B. So for A, you have the same latency because as this case. Why? Because you are reading from memory. But for B, B is already available by the time you need it in the L1 cache. So you don't need to go down to the memory. And for C, you will read C from here, right? And but then D will also be available, right? So what you are doing that for every second element, you are making it available all in advance in L1 by prefetching. So you are like as a rough estimate, you are speeding up, you are widening the latency, let's say by 2, because every second element is already in L1. It is not exact calculation, but if you want to give it just a rough estimate, right? So this is how like you can prefetch. Now coming to your question that how the data is prefetched, byte by byte or in blocks, it again depends upon what type of prefetcher you are using, or what are the like configurations of the prefetcher. Do you want to prefetch? How long you want to prefetch? 1 byte or 64 bytes, or what is the size of prefetching? Okay, so it can be different. It can be like a parameter of your prefetcher design. I hope I answer your question. If not, let me know, Asim.
Yes, thank you.
Okay, you're welcome. Okay, the other thing is like if you have identified the task, you have balanced them perfectly. You have done the data splitting in a way which is conducive for fast execution or low latency execution. The other thing you need to look for is data dependencies between the tasks. So again, let's say you have same application and you have identified 4 tasks. So now assume a situation where we have data dependency between different tasks, and the way we execute those tasks result in a situation where dependencies are not respected, right? So let me try to give you an example. Suppose that task 2 here in this figure, suppose that task 2, it must multiply each element of its input data with the sum created by the task 1 before summing the elements. So basically we are saying that task 1 calculates the partial sum, which is 1 plus 2 plus 3. But for task 2, we want each element to to be multiplied with the partial sum of 1 plus 2 plus 3, which is 6, right? So 6 times 4, 6 times 5, 6 times 6, and then get the partial sum of these elements after multiplying each one of them with 6, which means that task 2 must wait for task 1 to provide the partial sum, right? So there is a dependency. Task 2 cannot be completed before the task 1 is completed, right? And if we don't respect this dependency, and if we don't enforce it, what will happen? The task 2 will sum 4 plus 5 plus 6, which is not what we want. And as a result, we have erroneous overall result, right? So if there are dependencies in the application, then while we are implementing threads, we must make sure that those dependencies are met. Okay. Any questions? Another challenge with the parallel programming is that parallel programming or multi-threaded applications, they are extremely difficult to debug as compared to single-threaded application. And the reason behind difficulty of testing and debugging stems from their nature. The nature that they are threaded makes them difficult to be tested and debugged. So let me give you an example again. Let's say we still have same application, finding sum of all elements. We have 4 threads, right? And when we run our application, this multi-threaded application consisting of 5 threads, basically here we have task 5. So let's say there was something wrong in the code written for the thread 1, right? And as a result, it computed the wrong partial sum, right? Or maybe there was an error induced in the data, right? And as a result, we had erroneous partial sum, incorrect partial sum here, right? Let's say next time when we run the same application again, which is still multi-threaded, the error appears or something wrong happens with the thread 3. And this time the partial sum calculated by task 3 is wrong, and as a result, the overall result is incorrect, right? But if I'm looking only at the overall result, I will not be able to figure out that uh, what is the source of problem, which thread is malfunctioning or which thread is creating the incorrect result, right? And the problem is like I cannot, for example, predict that uh, which thread is going. I cannot. It will be difficult for me to create the same sequence of execution, right? So it is stemming from the fact that that maybe we are assuming that there is an error which appears at some times which appear in the execution of thread 1, but next time it doesn't, right? And there can be situations like that where maybe there are interdependencies, and sometime violating those dependencies result in erroneous results or incorrect results. uh, so it will become difficult because these multiple threads are interacting with each other. So it is extremely difficult as compared to single threaded application to do debugging and testing, because you cannot enforce the order, because it is up to the operating system how it is going to schedule those threads and on at what time and on what course. So testing and debugging is more challenging in multi-threaded applications than single-threaded applications. Okay, so until now we have talked about challenges of writing the multi-threaded applications or multi-threaded program. So like even if you have a problem, you first have to break down that problem into parallel tasks, and then you need to make sure that those tasks they are balanced in terms of like how long it takes for them to do their computation. Third, you need to make sure that data on which these tasks are operating, it is separated in such a way which is helpful in reducing the overall latency, right? And fourth, if there are dependencies among tasks, we must respect those dependencies. And then fifth is about testing and debugging, right? Now, what type of parallelism we can have when we are developing the multi-threaded application? There are main two types of parallelism. One is data parallelism, where we distribute the subsets of the same data across multiple cores, and then each core performs the same operation. So let's say, for example, it is same as what we have done in the previous slides, in the examples of the previous slide. You have data, and then you have like partitioned it into different chunks, right? And then you allocate that data to threads running on 4 different cores, core 0, 1, 2, and 3. So all the 4 cores, they are doing the same operation, and the same operation was summing the data, right? You are calculating the partial sum of the data allocated to you, right? So here we are not distributing the computation. We are not distributing the operations. All the threads are performing the same operation. We are distributing the data, right? The other is task parallelism. In task parallelism, what you do is that you uh, distribute the operations across different threads, and the data may be unique. Data could be same or different. So for example, here is the case. You have same data, right? And the same data is sent to all four cores, 1 2 3, but then they perform different operations. So for example, here this core is doing addition of all the elements in the array, and let's say this is simply multiplying all of them with a constant, right? And let's say this one is taking complement, let's say 2's complement of all the data elements, and core 3 is doing some other operation, right? So we are distributing the operations. So compare it with the case where you have a single threaded application. So then what you will do, first you will do summation of all the elements in the data array. Then you will do the multiplication with a constant for all the elements, let's say, and then you will do the 2 complement of all the elements and so on and so forth, right? So here what we are doing is that we are distributing the task in term of operation to multiple threads, 4 different threads. However, these two type of parallelism, any questions here? Any confusion? No? So these two type of parallelisms are not mutually exclusive, which basically mean that, for example, what you can do is that you can distribute the data and you can also distribute the task. For example, you can say, okay, I am segmenting this input data set into 4 parts, and then I want addition to be performed on the first one, and then I want let's say multiplication with the constant on the second segment, and then 2's complement with the third segment, and let's say exclusive or some other logical operation with the fourth segment, right? So now different data goes to different threads, and each thread also perform different operation on the data received. Any questions? Okay, now let's talk about Amdahl law and why we need to talk about Amdahl law. So basically, it answers this law help us to answer the following question: what potential performance gain, which basically means speed up, you can get if you have if you run your multi-threaded program with multiple cores, right? So one case is, let's say initially you had a application and it was single threaded, right? Now you have rewritten that application by identifying different tasks and assigning those tasks to different threads. So now it has become multi-threaded, and now you can run it on multiple cores, right? Now if you can run it, let's say you can run on 4 cores. Initially you were running on single core because you had a single thread, right? So how much speed up you can get as for the second case where you are using four cores with 4 threaded application as compared to the single threaded application. So we can answer this question by using the Amdahl's law, right? So here we are assuming an application or a program which has both serial and parallel parts. So serial parts are those which must be executed in sequence, and then there are some parts which can be performed in parallel. Like let's say here you have okay, I don't know if I can draw here. So let's say you have this program, and here you initialize an array, right? And after initializing, you say, okay, you have task 1, which is responsible for summing all the elements, task 2 for subtracting a constant from all the elements, task 3 for multiplying all the elements with a constant, and task 4 to complement all the elements, right? So but this part where you are doing the initialization, let's say it is sequential, and after that you can spawn 4 threads and then each thread takes care of one operation on the data, right? So this is serial part, this one is serial part, and then this part is this part here is parallel part, right? So we have an application which can be divided into both serial and the parallel parts. Now assume that the program executes and finishes in 1 unit time, right? And if it finishes it executes and finishes the execution in 1 time unit, so we denote the time to execute the serial portion of the program as S. So S will be greater than equal to 0 and less than equal to 1. So it will be equal to 1 when there is no parallel part, right? If there is no parallel part and all the program is executed in sequential way, then S will be equal to 1, which basically means that all of the execution time is consumed in executing the serial part, right? And if S is equal to 0, it will mean that there is no part of the program which is executed in serial and it has only parallelizable code, right? All of the code is parallelizable. But that will be like very difficult to find where S is equal to 0. It's mean that always S will be like most of the times S will have a non-zero value, right? So then 1 minus S is the runtime of the portion that can be parallelized, right? So if S is the time consumed in serial portion and total time is 1, then definitely 1 minus S is the runtime of the portion that can be parallelized, right? Now, let's assume that we have n number of processing cores. So it's mean that we can run n tasks in parallel, right? So it's mean that the parallelizable portion of the program, only this portion, because this indicates the parallel part of the program which can be run in like by running multiple threads. So if we have n tasks, then we can speed up only this part, right? Parallelizable part. So the parallelizable portion of the program, it will become n time faster if we have n cores, right? So here, for example, let's say I have the parallelizable program, but I have only two cores. Then I can run 4 tasks only on 2 cores. Now compare it with the case where I have 4 cores. Now I have 4 tasks and I can run them separately on 4 cores, right? So, but then I can speed up by using these increasing number of cores. I can speed only parallelizable part. I cannot I cannot speed up the execution of the serial part, right? Because it doesn't matter whether I have 1, 2, 4, or 8. This serial part must be executed in sequence, in a sequential way. So with that, we can achieve this, we can calculate the speed up by using this equation. So if 1 is the time, 1 is the total time which is needed for the execution of the program, right? And S is the serial part, and 1 minus S is the parallel part. So if we have n cores, we can divide 1 minus S by n to indicate that it is partitioned across n threads or n cores, right? So this will give us the speed up if you have a program with serial part S, parallel part 1 minus n, and which is then executed by using n cores. Any questions at this point? Any confusion about Amdahl's law? No, I'm like kind of surprised. Surprised, like you don't have questions about Amdahl's law. No confusion? Okay. So let's assume that we have S equal to 10% and N is equal to 2. So which basically mean that 10% of the application code is serial. It cannot be parallelized. And the remaining, which mean 90% can be parallelized, right? And we have 2 cores available. So then what will be the speed up compared to the case where we had all of the cores serial code, right? So the speed up will be 1.81 times. You can get it by simply plugging in the values. S is 10%, which is 0.10. 1 minus S is 90%, which is 0.90. N is 2. Plug in the values and you will get 1.81 times. Now compare it with the case where you have another application where 80% of the code is serial. You cannot parallelize it, right? So which means only 20% of the code is parallelizable. And you have 32 cores, right? So if now you plug in the values in this equation, your speed up will be 1.24 times. So do you see the difference? Here, the speed up in the first example, the speed up was 1.81 times, but here it is much less, 1.24 times. Although in the first case we were using only 2 cores, and here we are in the second we are using 32 cores, but still we are getting much less speed up, 1.24 as compared to 1.81. Why? Anyone want to answer? Anyone who want to answer? Or you want me to state the question again? Okay, let me state the question again and then try to answer it. Uh,
Or
okay, go ahead
first
if
of all,
you.
I was just gonna make a guess, but the speed up is significantly less because the majority of it is serialized. It must be done in sequence, as opposed to where
Yeah.
if we could run it in parallel, it would be much faster.
Yeah, because there is only 20% of the program which can be parallelized. So it doesn't matter whether you use 32 or 64. If there is, like, let's say, much less amount of work to do by simply increasing the number of workers from, let's say, 32 to 64, it will doesn't make much difference because there is much less amount of work to feed those workers, right?
Right.
So that's why you see only 1.25 times improvement. And actually, the same thing is stated by this graph here. So let me, first, let's have a look on x-axis where you have increasing number of processing cores. So basically, if you have 2 cores, you can run 2 threads in parallel. If you have 4, you can run 4 threads in parallel. If you have 16 cores, you can run 16 threads in parallel, right? And on y-axis, you have the speed up as compared to the case where you have uh, only sequential or single threaded process, right? And here you see the 4 different lines. So this pink line is for s is equal to 0.50, where basically we are saying that 50% of the code is sequential and 50% is parallelizable. Blue is where 10% of 0.10 or 10% of the code is sequential and 90% is parallelizable. And in green, 5% is sequential and 95% of the code is parallelizable, right? So what we see here is basically, or what is the takeaway from this graph is, like, if you have only lower the parallelizable part of the code or the application, lower will be the speed up as a result of increasing the number of cores. So for example, here when you go from 1 to 2, you achieve, I don't know, maybe 1.5 times improvement, right? And when you go up to 16 cores, you get less than 2% improvement because 50% of the code is serial and only 50% is parallelizable. But when you move to the blue line, 90% of the code is parallelizable. That's why you see much more improvement as compared to the pink line when you use 16 cores. And you see even more when you have 95% parallelizable code. And this is the ideal one where you have all the code is parallelizable and there is no sequential part. Okay. Any questions? So here you have actually, in the ideal case, you have linear speed up. As you keep increasing the number of cores, your speed up will keep increasing. Okay. Any questions? Okay. Now we have 1 minute left. So let me not start this new topic of, not new topic, but subtopic of threading sport. If you have any questions, let me know. If not, then that's it for today. And basically, then it means that we will cover in the midterm exam up till, including up to Ahmed's law, everything. Okay. And also one more thing. Today I will release module A of the project one. Okay. So keep an eye on the Canvas page. Okay, then that's it for now, and see you in the next lecture.
Thank you.
Thank you. Have a nice day.